Okay, so it's a great pleasure to be here. As Professor Liang said, I used to learn a lot from him when he was a postdoc and I was an undergrad student, and now it's a great pleasure to continue learning from him. So this is joint work with my student Xiaofan Xia and my wonderful collaborator Qin Li at Wisconsin. So the motivation that drives me to study the problem of fusion plasma is what do you think is the main bottleneck of modern AI? Some may say it's about algorithm. We can find better training algorithm, better architecture, and maybe data. As you know, like AI, like general model has used up all the data from the internet, and maybe one non-classical answer is electricity, and it's actually becoming increasingly important. Actually, even back in 2024, the global data center electricity consumption is already comparable to that of UK, and of course, over the recent 2 years, it's growing exponentially. And my dream was to make AI and fusion a perpetual motion machine that, imagine in an idealized world, maybe you can use AI to help nuclear fusion to generate an infinite amount of electric energy, and then use this electric energy to further train our AI model, and we are good. But the problem is, what can AI do for fusion energy, right? So that's the main theme of today's talk. And before discussing the control problem, let me first give a very short introduction about fusion energy. So this is a canonical fusion reaction diagram. As you can see, it's basically deuterium and tritium, some fusion reaction, and it releases a huge amount of power. And an important criteria in fusion energy is the so-called Lawson criteria. So basically, it's saying that in order for nuclear fusion reaction to be self-sustaining, you need to confine and control the fusion reaction with sufficient high density, sufficient high temperature, and you want to confine it for a reasonably long time. The product of the three needs to exceed some certain threshold. For example, the fusion reaction that is happening every day in the sun, it is happening with reasonably high density, and its temperature is, of course, it's high, but it's not as high as the fusion reaction happening in the commercial fusion reactors. And its confinement time is very high. And this kind of confinement is usually by the force of gravity. On the other extreme, we can consider another type of nuclear fusion that we can do, which is nuclear bombs. And it's extremely high density and extremely high temperature, but the reaction just finished all at once. It's impossible to collect commercially reusable energy from it. It's destructive. So one of the most promising commercial fusion reaction strategy is based on tokamak and accelerators. So for this kind of reactors, you need to confine the plasmas with sufficiently high temperature, reasonable high temperature, reasonable high density, and you want to confine it for a reasonably long time. And this kind of confinement is usually through electromagnetic confinement. And the key challenge with this kind of controlled fusion energy is actually something very much related to what we are doing in reinforcement learning and in AI in general. It's a stability issue. So basically, you can think of a tokamak reactor as basically some device that contains this extremely high temperature plasmas. It's charged particles. And you want to use some external electromagnetic field to keep the reaction to happen in a stable way within a reasonably long time period. And as the picture shows, there are actually two types of instability can happen. At a microscopic level, what could happen is that there are some, this plasma as a fluid, it may lead to some tearing, it may lead to some unstable shape that may ruin your reaction. But also at a microscopic level, there are some more like sophisticated story that can happen. So basically, even if the overall shape of this plasma system stays stable, it doesn't mean that you can confine it for a long enough time to satisfy this Lawson criteria, because there are some like electromagnetic interaction between these particles such that it may leads to some like microscopic instability that decrease your temperature and breaks down the Lawson criteria. So usually, if you don't control it carefully, the confinement can be lost very soon. So mathematically, how do we model this kind of thing? So we know that although it's a complicated system and it's also experiments are very costly, but actually there are something we can do because we know the physics of this kind of system relatively well. And so from first principles, actually we can derive some like interacting particle equations for this kind of fusion plasmas, and it's called the Vlasov Poisson equations. So to start with, you can consider a system of interacting particles following basically Newton's law, and their like interaction in terms of the electric field is basically governed by this Coulomb force. And now, if you write the phase space density, you can think of it as like joint density of the position variable and the velocity variable. It becomes like in general a six-dimensional density. So if you take this empirical density and take this mean field limit, you'll arrive at this like so-called Vlasov Poisson system. So it's a system of nonlinear PDEs. So F is your phase space density, it's the joint density of your position and velocity variable. And you'll see like two terms, the transport in terms of the location, the position part is just governed by the velocity, and the transport in terms of the velocity part is basically governed by the electric field, and this electric field itself depends on the current state of the system. So in general, as you can see, this is a nonlinear system of equations because E is multiplied with the gradient V of F, and E itself depends on F. It's actually solved through some partial differential equation from F. So actually, this kind of nonlinear dynamics and this kind of internal electric field leads to very serious instability problem. Actually, this is a very simple like illustration of actually a simplified model with a periodic condition and one-dimensional like reduction. So as you can see from this simulation study, if you don't make any control on the system, and even if the shape of this plasma system stay stable, within a very short period of time, what is happening is that the electric potential energy of this system can grow rapidly and soon like dominate the system energy. And that means if the electric potential energy grows, the temperature will decrease. And as you recall at the beginning, to meet the Lawson criteria, we need to keep the temperature sufficiently high for a sufficiently long time. And basically here, the growth of electric potential energy means the reaction may cease to happen within a short period of time. To visualize this type of instability, we can also draw a plot for this phase space density. So let's suppose we start with like some like density is actually small perturbation of this mixture of Gaussian density in the phase space. So in the X domain, it's near uniform. It's a near spatial homogeneous, and in the V domain, it's a mixture of two Gaussian. So that's actually widely used type of phase space density that people actually need to consider in plasma systems. And within a short period of time, what you will see is that it creates certain like turbulence and like finer and finer structure, and eventually it becomes very messy. So it's no longer preserved this clean two-stream structure. And that's also, if you see something like that, that's also an indicator that maybe this system is already unstable, and usually when like at the end of this time period, the reaction already ceased to happen. So on the other hand, so we have seen what it means to be unstable. On the other hand, what does it mean to be stable, right? So we can consider there are some like this kind of plasma system that may look like stable. So a nice candidate to compare with is the free transport equation, where you don't have this internal electric energy and internal electromagnetic interaction. And this is actually a nice system of, in terms of stability, this is actually a nice equation, because what is happening is that if you make some small perturbation on stationary density, the perturbation will be transformed into finer and finer scales, but it never grows. And so if you draw like animation, like it's basically the evolution of it, like on a torus may look like this. So at first it may be non-uniform, but after some time period it become like near uniform. So this may look like nice, and this is actually physically this corresponds to the so-called phenomena of phase mixing. So like some of you might be familiar with like this kind of Markov chain mixing or contractive dynamical systems, where there are some energy dissipation and there are some like contraction, like things get closer and closer under some norm. But here, this phase mixing phenomena, I would argue that if you look at this picture again, it's quite different. If you really look into its density diagram, you'll see that it's never get any energy dissipation. It's just the structure that gets transported into finer and finer scales, and eventually, on average, it may look like already mixing in this spatial domain. So if you move on from this linear, like very nice free transport system to Vlasov Poisson system, you'll find out that it's in general it's quite challenging to make it stable. So the stationary it's not hard to construct a stationary solution. Actually, any density that is spatially homogeneous is already a stationary solution to the Vlasov Poisson system. But the issue is that we are usually in the situation on the left side instead of the situation on the right side. One exception is the famous result by Muholt and Villani. Actually, this is one of the the major result that gives Cedric Villani the Fields Medal. He proved that if your initial distribution, if your stationary distribution is like nearly Gaussian, it's something very nice, then actually even if you run the uncontrolled dynamics, it's already stable. Like you don't need to impose any additional control. But unfortunately, if you want to make the problem relevant for fusion reaction, if you want to use realistic density such as the two-stream or bumping tail distributions, it actually violates the assumptions that Villani make for the nonlinear damping to hold true. And actually, through the simulation study I showed in the previous page, you'll see that it's actually the system itself is actually unstable. It's not a theoretical artifact. There are some real instability happening. So that's why we need a control. So let's now instead of considering this uncontrolled dynamics, let's try to apply some external electromagnetic field onto the system to try to make it more stable, right? So when you apply electromagnetic field, in terms of this equation, it's just you just add an additional like electric field term to this system, and of course, immediately, since we know that the free transport process itself is stable, a very naive solution, which actually works, is to use the electromagnetic field to exactly cancel the internal electromagnetic field, so that the system just behaves like a free transport equation. And actually, in theory, you can show that if you can do this, this actually works. You can show that if your initial density is case order smooth, then we'll see a polynomial decay in the total electric potential energy. And if your initial density is analytic, then you can mathematically show that the electric energy in the system is exponentially decaying. So you can also visualize it in this electric energy plot. As you can see, actually you'll see a rapid decay in the electric energy. And if you visualize it under using phase space density, you'll see what I mentioned as the phenomenon of phase mixing. So initially you have some like two streams with some small perturbation, and this perturbation never gets disappear. It's just being transported to finer and finer structures. But the overall shape of this distribution stays looking like a two stream. You never get something having this kind of weird turbulence. So this all looks like very nice, but what's the issue? Like why we are discussing the problem? Why we still think of nuclear fusion control as a hard problem? One aspect of the technical difficulty in practice is that in order to apply the idealized control policy, we need to know the solution to the PD. We need to know the F. But this F is the phase space density. It's a six-dimensional density of the particle. And it's never observed in practice. What you observe in practical plasma fusion applications is just a few sensor readings. And they are like very low dimensional projection of this complicated function space object. And the sensors are usually noisy, and they are also placed maybe sparsely inside the system. So here, for simplicity, we consider a simplified version of the sensor reading and experimental setup. So let's consider for each time you draw a random initial condition F0 independently. And for each run of the system, at each time k eta, at each time step, you get a noisy observation, noisy measurement of the density of the system. Sometimes you can also get a temperature measurement, but here for simplicity, we just consider like observation of the density, the position variable density. Actually, rho is the integral of f by integrating all the v variable. So basically, you get to like observe the physical density of the system at every sensor location xi and every time step k eta. And this observation is noisy. And our goal is to predict the control policy based only on these sensor readings. And we want to achieve real-time control. Of course, we are not the first one to study this problem, and in both like classical like fusion plasma and inverse problem literature and in machine learning literature, there are already some existing work on this. Like, since we are working with a partially observed system, a natural idea coming from partially observed control is to estimate the state, to solve the inverse problem and try to reconstruct the current state of the system based on the sensor readings. And this leads to a sequence of work in terms of plasma diagnostics, and there are also work that move on from inverse problem to control problem. But I would argue that this may not be the most efficient approach to this problem. There are a few limitations. First, the plasma system is happening at a very small time scale. Things are very, very fast. And if you try to estimate the state by solving an inverse problem, it's usually computationally expensive, and you don't want to spend a lot of time solving this inverse problem to control the state. On the other hand, I would argue that reconstructing the state itself may be doing too much for just controlling the stability of the system. Because, as we said, the ultimate goal is just to predict the control action. And if you reconstruct the full phase space density, it's doing too much. Like Richard Sutton, the father of reinforcement learning, said, we should always approximate the solution to the problem instead of the problem itself. So probably we could try some more like end-to-end learning-based approach. And there are actually some existing work, mostly done by Google Demand and their collaborators, that use reinformed learning to control the stability of plasma systems. But they are actually controlling more at a microscopic level, controlling fluid dynamics stability. And the kinetic instability phenomenon we were mentioning are less explored in this area. And second, they are ignoring the underlying equations that gives us a lot of knowledge. But our approach is try to incorporate the flexibility of learning with the known PD structure that gives us the knowledge. So now here comes our methodology. We are trying to use a machine learning method called imitation learning to apply to this kind of partially observed systems. Imitation learning is not a very new concept in machine learning. For example, like if you train a self-driving car, basically you can try to mimic the expert driver's demonstration. And here we are not doing some robotics or like mimicking human demonstration, but instead we can see the solution to this partial differential equation with full state observation as the expert demonstration. And our agent can only use sensor reading information and tries to map the sensor reading information in some past history to the control action. Okay, so that's a very, very standard approach. And of course, like when you collect the data, you can either use this expert trajectories or you can use the controller's own trajectory. And they are available through simulations. And we consider two types of loss functions for imitation learning. The simplest version is so-called behavior cloning loss, right? You can just get the fully controlled trajectories from simulation. It's essentially a free transfer equation. And then you can just minimize the error, the difference between our prediction and the optimal control policy on their control trajectories. But alternatively, you can also consider another loss function called online imitation learning loss. So in such a case, you don't use the expert trajectories, but you want to minimize the error between our prediction and the ground truth under our own trajectories. So this, you can think of this somehow solves the distribution shift problem. But later in this talk, we'll discuss which loss function is better and why. So now, let's maybe before diving into the theory, and let's first look at some simulation study we did. Actually, this is through behavior cloning, and we train it with a neural network on 5,000 trajectories in the simulation environment. And we'll see that the electric potential energy is actually not really decaying all the way down to zero. It's not increasing either. And maybe it doesn't look like very good from the plot itself, but if you recall that our original goal is not to make the electric potential energy extremely small, but our goal is to avoid the electric potential energy to blow up so that the temperature of the system can stay high. This already achieved that goal. And if you visualize it through phase space density, you'll see that if you start from something like a two-stream and you run it for some time period, actually it stays close to two-stream for a long time period. So we also did simulation in some harder regimes where we can further reduce the number of sensors, for example. If you get less information to control the system, you'll see that the neural control obtained by our training method make the system stable for some time period, but eventually the electric potential energy still blows up. And in phase space density visualization, you'll also see that it gets stable for at least much longer than the uncontrolled trajectory, but after some period, you still see some blow up. But I would argue that perhaps this is okay because this, like if you control it for sufficiently long time, it already meets the Lawson criteria and the reaction is self-sustaining. We also compare our method with some like baseline that is not based on learning. So if you don't try to learn it, but instead you just try to reconstruct the state using sensor reading and just solve the PDE, it leads to this orange line correspond to a baseline technique. And as you see in this like hard initial condition problem, actually this baseline is breaking down faster than our method, and we can still control it for reasonably long time period. And as you can see in the phase-based visualization, our method also stays close to two stream for longer time. So that's some like simulation and some demonstration of our method. And note that today's talk is the provable imitation learning for partially observed Vlasov Poisson equation. So we also want to understand the fundamental possibility of this learning-based approach, and we want to do some theory. Okay, so what are the key theoretical questions that we could ask? The first question is like straightforward one. So remember that when we try to minimize imitation learning loss function, we are just doing some optimization. It doesn't necessarily mean, even if we can do the optimization well, it doesn't necessarily mean that we can do we can perform good control. So the question is, does small imitation learning loss actually imply stabilization of the system? And second question is, so recall that we are just trying to use a few sensor readings to predict the control action. So it could be very much possible that the sensor reading doesn't even contain enough information about what control action you should take. And what is the fundamental limitation of this approach, and when is this kind of information learnable through sensor reading information? Right? And the last question is about learning algorithm. So recall that we discussed like two choices of learning algorithm, online and offline versions of imitation learning, and which one should we use, which objective we should optimize, and how to optimize them. Okay, so centering at the center of these three questions is this K quantity, which is the optimal imitation learning loss function. Of course, like you may choose different versions of the loss function, but the optimal imitation learning loss function within some policy class. And now let's look at the first question. Does small imitation learning loss actually lead to stabilization of the system? So actually we show that for behavior cloning, the answer is yes, but at some cost. You can show that if you learn a policy using behavior cloning, and you actually get to see some exponential decay in the electric potential energy as the expert control policy achieves. But there are some additional error floor induced by your loss in the behavior cloning, and this error floor is amplified with a CT factor that may grow with T. So in some sense, behavior cloning actually works for this kind of phase mixing systems, but a caveat here is that this CT as a function of T may be exponentially growing with time. So you can control the system to be stable for some time period, but not for a very long time period. And if you like, you can also study when we can make this population level behavior cloning loss small by like achieving small sample level behavior cloning loss. Okay, so I guess that's partially, at least partially answer the first question. And now, how about the second question? It's a more subtle question. Like, when is this kind of information predictable from sensor readings, right? So to answer this question, actually we start with two extremal cases. So let's suppose if your initial distribution F0 of the system is deterministic. This is actually the favorable situation for inverse problem approach. For this kind of approach, you can simply like reconstruct the initial distribution and just forward solve this PDE. And the solution to this PDE gives you the control policy to use. And you don't even need to use a closed loop control that's based on sensor readings. You can even use an open loop control. On the other hand, the more random the initial state is, the harder the control problem becomes, because it gives you more degree of freedom that you need to cover. So to interpolate between these two cases, we use the entropy of the initial condition as the key criteria. So note that the initial distribution itself is a function. It lies in some function space. So it doesn't have a well-defined notion of entropy as discrete random variables. So here we use a scale-sensitive version of entropy as shown here. And it's a kind of, we can argue that it's probably a nice quantity. It's a natural quantity to consider. It's a generalization of differential entropy to function spaces, and it's you can think of it as a probabilistic version of a covering number. So based on this notion of epsilon scale entropy, actually we can show a theoretical result about the fundamental possibility of learning this kind of a control based only on sensor readings. So this result itself may look like a bit abstract at first glance, but essentially this is saying that we have a good policy class such that its imitation learning loss is bounded by some statistical error and some discretization error. And now let's take a closer look at these two error terms. The statistical error is essentially the statistical complexity of this initial distribution with this it's basically the estimation error for reconstructing the initial distribution from direct observations. But here we only have indirect observations. And the noise level is sigma squared by k, where sigma squared itself is the sensor reading noise level, and k is some constant to be determined. And the discretization error term appearing in the second term is essentially saying that there are some, since you only use sensor reading information, of course, like you may be covering the space only partially, and there are some discretization error. And importantly, this k eta to the 2p is basically the cost of reconstructing the future state of the system based on past information. And as you can see, the constant integer, the integer k is used to balance these two terms. Larger k becomes the signal to noise ratio in the statistical complexity becomes better, but you also suffer from larger discretization error. So this is basically capturing the temporal aggregation effect in this kind of learnability question. So if you use longer history to reconstruct the control policy, then basically the older data may still help you reduce the variance, but on the other hand, it may lead to some bias because the older data looks very different from the newer data. So also it's worth noting that this is just a constructive proof of the theoretical upper bound. It's just saying that if you can find some like k and epsilon to make these two terms small, like basically intuitively, if the statistical complexity of the system is small, and if you also suffer from a small discretization error, then actually there exists some nice control policy that actually works. But operationally, you don't need to explicitly find it. You just train a neural network. Question? Eta is the discretization step size, the observation frequency. Yeah. At every eta time, you get a new observation. Yeah. Sorry? K is the history dance. Yes. So let's address the second question. And now the last one, which loss function should we use for this imitation learning problem? So recall that the behavior cloning loss guarantee that we presented at the beginning. As I said, the constant CT may be exponentially growing with t in general. But like when we first proved this result, I was wondering, is it a proof artifact or is something fundamental to these plasma systems? So my first intuition came from a finite dimensional linear system. This is like classical object in control theory. If you consider a stabilizable finite dimensional linear dynamical system, actually you can do some similar calculation and suppose that you have some policy based on some linear policy that achieves small behavior cloning loss. Actually, you can show that theoretically it won't suffer from this kind of exponential blow up in the error compounding. Actually, there's no error compounding at all. If you can make behavior cloning loss epsilon, and if this epsilon is sufficiently small, then you can show that the stability of the controlled system is actually exponential decay. It satisfies an exponential decaying bound plus something that is offered epsilon and not increasing with t. Is this the case also for this kind of plasma system in infinite dimensional space? So unfortunately, this is not true. And we prove a negative result showing that no matter how small the error is, as long as you have some error in the behavior cloning loss, this error, if you deploy this policy, this error can always be exponentially amplified as time grows. So basically, even if you can make behavior cloning loss really small for epsilon, it can stabilize the system for a while, but it can only stabilize the system of order log 1 by epsilon time. It works to some degree, but it doesn't work as good as you expect. And that may also be related to the eventual blow up in the simulation that we have observed. So this is in sharp contrast with the finite dimensional linear system, and I would argue that this is some intrinsic property of this kind of infinite dimensional kinetic equations. So to overcome this limitation, we can move on from a behavior cloning loss objective to online imitation learning loss. Right? You can consider, like, if you partially solve this distribution shift problem and try to control the system to be stable on our own, we want to imitate the optimal policy's behavior on our own trajectories, then what will you get? So basically, online imitation learning loss asks us to imitate the expert at trajectories where the learner itself goes. And actually, we have a relatively positive theoretical results if you can make the online imitation learning loss small. You can theoretically show that if the online imitation learning loss is of order epsilon, then you can you still suffer, your electric energy field still suffer from some error compounding as time grows, but this error compounding is only polynomially growing instead of exponentially. So that means basically you can make this loss of order epsilon, then theoretically you can probably stabilize this system for poly 1 by epsilon time period. And the last question is how to optimize this online imitation learning loss function. So in general, you can think of online imitation learning loss as a fixed point problem. So like you collect data from some policy and you want to minimize the error against the optimal policy on this trajectory. So of course, since it's a fixed point problem, you could run fixed point iteration, but turn out that the fixed point iteration itself is not very stable. So we use a variant of this kind of fixed point iteration style method. It's called a classical method called dagger. So we use a variant of dagger. In each time of the fixed point iteration procedure, we use a mixture of our own policy and the optimal policy we are trying to imitate to collect the data. So in simulation study, it turned out that this dagger method actually achieves stability within much longer time period. As you can see, this blue and the purple lines are the policy, are the electric field energy for policies learned using behavior cloning with different parameter setups. And this red curve corresponds to the electric field energy of the policy learned from dagger. As you can see, it's just keep the system stable for a longer time. And you can similarly try to visualize this instability phenomena and the stabilization in the phase space density. As you can see, the uncontrolled policy, of course, it gets blow up very quickly, and expert policy just stays very stable for a long time. And for a different version of dagger, you'll see some finer structure that's creating some turbulence within certain time period. It's better than the uncontrolled and better than the non-adaptive, non-learning baseline, but it's at least for this simulation, it's worse than dagger, which achieves the best performance. So let me summarize this talk through a discussion and the future works. So plasma, this is a very specialized study on plasma fusion. But I would argue that this is probably a very important problem. Actually, Kasabi said it's a root node problem because it helps us, by investigating the problem itself, it helps us develop theory and algorithms for a new class of physical systems that may be also useful for other different purposes. And in practice, this is a new class of algorithm that for important engineering task. And in the future, there are, of course, a lot of important directions. So currently, we are doing simulation studies on a relatively reduced and simplified model. But of course, it is important to scale up to realistic problem scales and real data. And actually, many of our ongoing work is to build up the fundamental, tools for this scaled up simulation and also the simulation that matches with data distributions. And an interesting statistical question that I didn't mention too much, but it's actually very important, is to learn the initial distribution from the data. Note that here, in order to simulate from the system, we need to know the initial distribution, or we need to be able to sample from the initial distribution. This is a kind of an unrealistic assumption in practice. And currently, we are working on learning the initial distribution of the system, actually learn to generate initial distributions using trajectory observation data. And also it is interesting to generalize our control idea to other physical partially observed systems such as quantum systems and fluid dynamics. Actually, this morning I talked to Professor Cao and we had some very nice discussion on fluid dynamics, and I hope to extend our study to further problems. Okay, so that's all for today's talk. Thanks for listening. I'm happy to take more questions. Yes.
Yeah, question? Yeah.
Thanks a lot, Wenlong. It's very interesting. I got a bunch of questions, so I'm going to start from what you are discussing. So you do mention like the initial distribution nu 0 is not very clear, and it's also appear in your upper bound because this directly controls your statistical error.
Yep.
So I think the initial distribution is purely physical, right? So as a statistician, we have no control over that.
Right.
So, but do you have any physical intuition, statistical intuition, like how large when you actually need the entropy, how large is auto entropy?
Actually, that's a great question. That's related to the initial distribution estimation question from here. So maybe let me first discuss the physical side and then discuss the learning side. From physical side, of course, if you try to build a reactor, you want to make maybe the particle beams that you inject into the system as accurate as possible. So actually, this two-stream density, as shown here, is coming from like basically two beams that goes at opposite directions. And if this is already very accurate, then you have less randomness in your initial distribution. But of course, in practical physical systems, it's not possible to make it very exactly as what you want. So there are always some errors. So that's one aspect of this. And on the let's say the learning side, actually we recently found some very interesting property that, so here theoretically we show that this entropy of the initial distribution enables control, enables the learnability of this control policy. And on the other hand, we also recently observed that this quantity also enables the learnability of the initial distribution itself. Under certain regimes. So basically that two sides of the story matches. And I mean, in physics, of course, this depends on your hardware, and there are some systems that this quantity is small and things are easy for both the learning of the initial distribution and learning of the control. And there are some physical systems that you have highly random nu 0, and maybe this problem is intrinsically hard for both sides. But I would argue that this is probably the right quantity to look at.
Okay, so I'm not good in physics, but maybe a little bit because if you, I wonder what's the scale you are talking about the physics system. If you go to particle scale, then you always have a certain amount of uncertainty. You cannot eliminate that.
Right.
So are we at this scale?
So that's a very good question. Actually, there's like extremely like microscopic scale of particle systems, and we are not in that region.
Okay.
But on the other hand, there are also extremely like microscopic scales like fluid dynamics, the overall shape of this.
We are also not there.
We are also not there. We are in between.
Interesting.
Yeah. And that's also where the difficulty comes from. Actually, the shape control is relatively. It's still not solved yet. It's still an active research area, but it's relatively well studied, and actually the current commercial reactor can control the shape for a relatively long time. But here, this problem is more subtle and less understood.
Okay, the second question concerns the dynamic system, because you mentioned like this highly nonlinear dynamic system is not contractive. I'm not sure if that's a good word to use that, but that's an MCMC word. So my question is, do you think the non-contractive nature is general for this kind of infinite dimensional system, or it's specific for this infinite dimensional system? And if it's later case, what's the physical intuition behind that?
That's a great question. So actually, I didn't spend too much time on this visualization of phase mixing, but so maybe an intuition is that maybe you have seen this like brain-teaser question that sorry, I think it's here. So there's a brain-teaser question like if you have a frog jumping on a unit circle, if the step length of this frog is the irrational multiple of pi, then like after it's jumping like for a long enough time, it's eventually trajectory covering the entire space. So as you can see, this is a purely deterministic system. There's no like dissipation. There's no like this kind of randomness, no diffusive behavior at all. But this system is still like mixing in some sense. And this phase mixing is you can think of it as a continuous analog of this frog jumping example.
So it seems to be, it should be contractive?
It's not. It's not. So it preserves the norm. The norm is always stays the same.
But then on the state level, it's not contractive.
So basically, the thing is that here you are looking at f, which is a density function in the xv space.
Okay.
And in that space, there's basically no contraction at all. The norm is preserved. But if you look at the marginal x distribution,
okay,
then it becomes decaying. So this is not some real decaying of the physics. It's just things get mixed, like at finer and finer scales.
Okay, thanks. So maybe the last question is about, you mentioned in the beginning is we should always approximate a solution rather than the problem.
Yep.
Now, I think what you did here, you find an expert, which is exactly what cancel the stuff, and then you try to approximate the expert, which is solve the problem. But now my concern is the expert is just one of the many solvers that solve the system. So you are not able to approximate the expert perfectly well, which you have this exponential growth time with t. Doesn't mean you cannot approximate the other one of the equivalent solutions.
You mean we could probably approximate some other control policy instead of this particular control policy?
So I mean, yes, there should be, my intuition should be many policies should work.
Yep.
We are just restraining our attention to this expert.
Yep.
Is it necessary?
Oh, that's actually a very great question. Actually, we have, I didn't put it in the slide because I don't have enough time, but actually we have done some experimental study on imitating other policies. And there's actually a good reason for that because there are many, as you said, there are many policies that can stabilize the system.
Yep.
And then if you try to compare these policies, you compare their energy consumption. And actually we found that if you use reinforcement learning instead of directly solving the PDE, you can actually save maybe 20–30% of the energy consumption compared to this. I mean, it's better in that sense, but on the other hand, it turned out that the policy learned from learned from reinforcement learning to control the stability. Compared to this exact cancellation policy, they are harder for imitation learning to learn. Okay. That's an interesting phenomenon that we don't have a full theoretical explanation, but the intuition is that this kind of policies are less robust compared to the exact cancellation policy that is solved from PDE itself. So maybe one more is, can we stop learning any policy but just set a loss as the total electrical energy and to optimize that? Yeah, actually that's what we are doing. Okay. Yeah, that's what we are doing for that. For that reinforcement learning task, but. Just the engineering side is not yet working, I guess. It works to some degree. Okay. But it makes the problem, it makes the picture more complicated. Okay. Yeah, thanks a lot. Probably took too much time, but. No problem. These are very, very insightful questions.
Yeah, we still have quite a few minutes of time. So any questions?
So forgive me, Professor, I haven't done physics in like 10–15 years, so but is it common to assume like a collisionless systems for problems like these?
Oh, that's a good question. So, of course, from the question, I see that you know physics quite well. So here, in nuclear, in this kind of physical modeling, it's it's always a matter of the temporal and the spatial scales that physical phenomena is happening. So here we are considering nuclear fusion, which are extremely high temperature plasma. And in that kind of system, the collision effect is not the dominating physical effect. So it's actually quite natural to ignore that in physics.
Yeah. Just one more question on top of that. So like, this is incredible work, but I also feel that like studying plasma is very complex, right? So I'm just wondering why not maybe go for something slightly easier so that we can answer the other questions like the error compounding effect and everything, and then maybe slowly move to something as complex as, I guess that just helps us answer.
What's the easier, maybe fluid or?
I didn't say it out loud, but yeah, maybe, I don't know.
Yeah, that's a good question. Actually, so I would probably say it's, I mean, like this system is derived from first principles. This is the kind of, I wouldn't say it's exactly correct. For example, we ignore the collision term, but this is more like more or less the accurate physical description of what is actually happening. But we can consider different levels of reduced order models. For example, you can, if you ignore the kinetic effect, you can consider like MHD equation, magnetic hydrodynamics systems. I mean, the control problem on that side is it's also studied in some existing literature, but they cannot capture this kind of microscopic instability effect, and that's part of our main motivation of the study. So I mean, so what do I mean by like considering MHD equation? Is essentially, so here we consider the conditional distribution of the velocity given the position as an arbitrary distribution, and it's here like the canonical choice is 2, 3. If you consider MHD, it's basically a reduced order closure, and in such a case, it's basically your conditional distribution of velocity given the position needs to be in a very restricted family, maybe some Gaussian distribution, and then it cannot capture this kind of kinetic instability effect. So in order to capture this kind of a technical challenge, we have to go to this kinetic systems. But then the question is how to simulate. This is actually simulating a 1D system, like in a simplified system. This simplification has some physical intuition. It's basically based on some symmetry reduction and a strong external magnetic field of the system. But of course, it's just an approximation to the ground truth. So maybe the right question to ask is, can we scale up to 3D, and then this kinetic system becomes extremely expensive even to simulate? And currently, we are also working on better AI-driven methods to simulate this system. Yeah.
Thank you.
Thank you.
Yeah. Yeah.
Just a small question. Yeah. So I'm not sure, like in the baseline, the green line in the the energy map, whether it's driven by taking H to be the negative of the electric field E. So I wonder, it's
which one? This one? Last one?
Yeah,
or?
it's like the energy grid. Yeah. So if we all know that in a free transport scheme where the H is just the negative of E, it's of course stable. But by analog of a forced vibration or forced oscillation, a physical principle. So is this possible that if we assert an artificial electric field to sort of force the stability of the whole dynamic system, is it possible to achieve the sort of stability by taking H as a very large and a very, I would say, a very controlling or forcing electric field such that the whole system is even more stable than the expert case where the H is just the negative, the vanilla negative of E. Yeah.
I guess we can discuss some details offline, but one thing that I would like to mention is that here actually we are already, so the fact that we are working with this one-dimensional reduced order model is already coming from taking a strong external magnetic field and under some symmetry reduction, we can work with this 1D model. So I guess maybe the strong external field thing that you are mentioning is partially already contained, although I didn't mention it explicitly, but it's implicit in this simulation setup. Yeah.
Oh, okay, thanks.
Thank you. There's more question.
Thank you for making the talk so accessible. My question is that I think the main problem is a sensor inference problem. I know that semi-definite programming is widely used in this field, so I'm wondering if SDP can be of use in this particular situation.
Actually, maybe we can discuss later offline. I'm not sure what exactly what type of SDP problem you are considering, but I guess in general, if your SDP dimension becomes high, it becomes computationally quite expensive. And if you want to achieve real-time control, it's sometimes costly compared to this kind of neural network approach, where at each time we just run a feed forward.